Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 31st, 2025, about 3 days ago. It introduces a method that allows large language models to process inputs up to 2 orders of magnitude beyond their standard context limits, successfully handling over 10 million tokens. The paper is titled Recursive Language Models, and as we'll see later, the performance gains on complex reasoning benchmarks are quite significant compared to traditional methods. So Figure 1 compares standard inference against this new approach. The left panel plots GPT-5's accuracy, showing a sharp decline for complex tasks like oolong as inputs get longer. Notice the red zone, where inputs exceed the model's memory entirely. In contrast, the right panel shows the recursive language model maintaining strong performance throughout. It even succeeds in the green region on the far right, processing input lengths that are physically impossible for the base model to ingest at once. Well, Figure 2 details the architecture that makes this possible. The main agent, shown in the large left panel, treats the long prompt not as immediate input tokens, but as a variable stored in an external Python environment. Inside the central terminal block, the language model writes code to inspect or split that text, rather than reading it all at once. Crucially, the arrows pointing right show how it handles complexity. The model programmatically spawns new recursive instances of itself to process specific data chunks. These sub-agents return their findings, allowing the root model to synthesize a final answer without ever fitting the entire document into its active memory. Alright, well, Figure 2 outlined the system. Table 1 now quantifies the results across 4 major benchmarks. The columns display tasks of increasing length and difficulty, ranging from code QA up to browse comp plus, which involves millions of tokens. If we look at the GPT-5 section at the bottom, the base model scores 0 on the massive browse comp task due to context limits. However, the recursive language model achieves a remarkable 91% accuracy there. Similarly, on the complex oolong pairs task to the far right, the method scores 58%, vastly outperforming standard retrieval agents. So, naturally one might worry that all this recursion drives up the bill. Figure 3 addresses this by plotting the cost distribution for GPT-5 on the left and QN3 coder on the right. At the median, or 50th percentile, the recursive language model in orange is surprisingly efficient, often matching the low cost of the base model. However, look at the 95th percentile. Here, costs jump significantly because complex queries spawn deep execution traces. Yet, even this tail cost is generally lower than the summary agent in purple, which must ingest the entire text every time. Moving on to Figure 4, we see code snippets that illustrate the model's emergent strategies. In panel A on the left, the model demonstrates filtering. Instead of reading the whole text, it writes a Python script to scan for keywords and retrieve only relevant snippets. Then, panel B on the top right shows decomposition, where the model loops through data batches and recursively calls a submodel for each chunk. Finally, panel C shows result stitching, combining those outputs into a final answer that exceeds normal token limits. Well, Figure 10 tests scaling on the browse comp plus benchmark. The left panel tracks accuracy, where standard GPT-5 in red crashes to near 0 as the document count hits 1000. In contrast, the recursive language model, shown by the solid teal line, maintains essentially perfect performance throughout. Meanwhile, the right panel reveals that the React agent in purple becomes extremely expensive, skyrocketing over $2, whereas the recursive approach remains far more cost-effective at half the price. Wrapping up, 2 takeaways stand out. Treating prompts as external data for symbolic manipulation allows models to scale effectively infinitely, and recursive decomposition proves far more robust than standard context compression. This points toward a future where smart inference strategies matter more than raw memory size. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.